Okay, good morning, everyone. So let's get started with what I believe is the last lecture. On Thursday, let me just maybe a bit of logistics. So this is lecture 11, which is again on the scattering transform, continued. Beyond. So I believe that we're this Thursday, we are meeting for the last time. And I think the planning for this Thursday is to discuss open questions. But I think I was wondering if we could maybe just do like a conversation, right? So maybe what would be great is that maybe each of you think a little bit what is the thing that you enjoy the most from this class, or what is the question or direction that you think most interested about, and we can maybe discuss about it on Thursday. Discuss a little bit about where the field is going and whether the kind of the outstanding mathematical questions that are raised by this story. Okay, so but now let's stick with today. So last Tuesday, last lecture, we discussed a little bit about basic and alternative route towards invariant representation. And maybe I will ask, okay, I'm the host. I see some noise. I'm just going to mute everyone. Okay, perfect. Okay, so we saw a route towards invariant representation that was using local operators. And we started to discuss a particular family of these operators that were wavelet transforms, right? So we saw wavelets, and their associated Littlewood Valley transforms. And I think this is where we stopped. So, and maybe it's a good point or a good time now to recap where we are, right? So in terms of the reason why we are talking about all this is that we would like to, we are really interested in building what we call invariant or invariant, and then so we have let me just write it like this. So we have single representations for high dimensional learning. And we discussed basically about 3 ingredients that we want in our wish list, right? So in the wish list, we discussed about 3 properties that were kind of critical, right? So the first property is certain invariance with respect to a known group of symmetries. We discussed about stability to call it near symmetries. So in the case of images, that was small deformations. And we also, of course, need to complement these two properties with what we call expressivity, or in other words, the ability to capture high frequency. Okay, so we don't want a representation that simply just destroys the high frequency information. Oh. Okay. And so last week, it's actually two lectures ago. So far, we have seen two routes, two ways to build invariant representations, two different constructions. So the first construction, that was via the Stone theorem, if you remember. So we decided that phi of x was the modulus of a certain Fourier transform, and that was kind of what we call the Fourier transform of the group. And we saw through this theorem that there was a one-to-one correspondence between a group that had certain nice abelian structure and these self-adjoint operators that admit this kind of Fourier transform. Okay. And we concluded last week that, so what are the properties that these representations satisfy? So in terms of in terms of the wish list, so does this representation satisfy the first requirement? Just checking that people are following.
Yeah, it was invariant.
Yes, good. Okay. Does this representation satisfy the stability to near symmetries? That's what we computed last week. That was the failure, like in the case of Fourier, right? So that was the failure that we described last week, that when you have a modulus of the Fourier transform, high frequencies become unstable, right? Even for a very slight transformation that is almost like a translation. And we also argued, we didn't show the results, but we also argued that just keeping the phase, like throwing the phase in the Fourier domain, is very dangerous, right? It can actually throw information, right? So basically, this is phase in Fourier retains, or like encodes rich information. So if we throw it, we are basically throwing away a lot of information from the signal, right? So we want to use this representation to learn properties from that are in the input, right? So we don't want to throw information. Okay, so that's what we were in the Stone theorem. And then we saw an alternative route, that's the thing where we left it, that was via what we'll call now in some recent work that we are building, we call this the geometric deep learning blueprint. Okay, and this is where the scattering transform is inscribed, right? And so we are gonna just refresh the idea on what is the kind of the architecture of this representation. Okay, and this blueprint is interesting for many reasons. The first one is that it really starts, so it has two ideas, right? Two ideas. And two principles. The first one is understanding basically the linear invariance and equivariance of the group. And then there's also like a notion of amongst all these linear invariants and equivariants, we're going to use them in a certain way, right? So we are going to combine them, in a nice way, through this notion of like spatial locality. Yeah, we are going to just refresh the architecture of this property. Okay, we are going to see now more in a bit. Okay, but before going into the details, let me just basically outline what is the main principle of this blueprint, right? So the point is that we are we are going to build a representation by combining building blocks. And so there's different building blocks. So I can have let's call them like this. A is any linear invariant operator with respect to G. So what does it mean? Is that A apply to the transformation, remember that we call it dg of x is equal to A of x for all x and for all G in the group. So we are going to consider A is one such operator. Then we are going to consider also B, that is any linear equivariant operator G. So this is an operator. So A, you can think that A goes from X to maybe some space that doesn't need to be indexed by the group. So A can be from, just to think of in terms of something concrete, is a scalar function defined over the input domain, and B can go from X of omega and certain channels, let's see, to X of omega with maybe C prime, right? So in other words, B is an operator that maps signals to signals. Okay, and so equivariant means that it commutes with the group. B of dg of x is equals to dg of b of x. And then finally, we complement this with C, if you want, any pointwise nonlinear operator. Okay, so C goes from X of omega C to X of omega C prime, right? And the property is that C of X at pixel U, this has to be just a function of X of U. Okay, so this is a mapping that again maps signals to signals, but with a very strong property that it's basically diagonal, right? So it only, like the output at a given coordinate only depends on the input at that coordinate, right? It can depend in an arbitrary nonlinear way, but that's the condition. And so now the question for you is, can we combine these three building blocks to build invariant representations? So obviously, in my family, in my dictionary of things that I can play with, so I have A, I have B, and I have C. Okay. So of course, I have A already, right? So I can take, for example, phi of x. That is just A of x. That we saw that last week, last lecture, right? So that, for example, in the case of the translation group, could be the average of the signal. right? Remember that we are really focusing on linear structure, right? So understanding linear operators that have some nice combination with the group is a much simpler question than understanding general nonlinear operators that commute with the group, right? So for the translation group, we have a pretty good understanding, like a complete understanding of what are all these operators, right? And the same thing goes for many other groups, that all the groups that we might care about in machine learning. Okay, so A of X is one example where you get invariance. But now, of course, let me just, let's start playing. So if I do B of X, do I get invariance? Obviously no, because B by definition is commuting with the group, right? It's not invariant. So what can I do? Can I, for example, take B and concatenate it with A? What do I get here? So remember when we said last time, right, is that the linear invariant structure in a group is typically very small, right? In the case of translation, there's only one operator that has this property, right? So A concatenated by B is probably an operator that is kind of the trivial operator, right? It has no range at all, right? Think about this as just keeping the low frequencies, and this is any convolution, right? So basically the only thing that survives is the low pass, right? So this is not a good idea, right? So this doesn't add anything. But now let's do something instead. What can we do to repair this mistake? We have another operator, we have another tool in our family, right? Someone can guess what can we do to recover some non-trivial invariance? Well, so far we have only used A and B. So how about we use C as well?
You compose with C this BX?
Yes, very good. So you compose it with C, and now you can use A, right?
Mm-hmm. Yeah.
Let's verify that this is indeed invariant. That's a good. So let's verify. That ACB is G invariant. So what do we need to do? We need to hit A, C, and B with some transformation of the group, right? So first we use the equivariance of B. So this is A, C, DG, BX. Now, because this operator C is pointwise, what happens when you combine a transformation in the domain with an operator that is elementwise, that is pointwise? So think about an image, right? You have an operator that is just taking any information you have at every pixel and changing it by the same function all the time, right? This function is always the same function, right? Does not depend on you, right? So you have the same, think it as you are changing the colors. Now you have an operator that is just moving pixels around, right? That is changing the location of the pixels. So if you deform your image and you change the colors, do you get the same object than if you first change the colors and then you deform the image? Anyone is convinced? Yeah, of course you get the same thing, right? Because this is element-wise. You get A, DG, C, and B. And now we can use the fact that A is invariant. Right, so you get the same as A, C, B of X. Right? So this is indeed a very natural way to construct more invariants. And more, not only that, it suddenly opens the box for you to do, basically to play with your imagination, right? I mean, we have done this thing once, right? But now we could do, A, C, B, C, B, X, right? And we could, if we have several, this is true for any operator, that any A, C, and B that are satisfy these properties, right? So any A that is invariant, any B that is equivariant, and any C that is element-wise. As it turns out, the family of B's, right, like the family of linear equivariants, is very large, right? Asking for a matrix to commute with the group, in fact, is a much weaker thing to ask than asking the function, like the operator, to be invariant. Okay, so we are going to see that we can actually gain a lot from that. So any questions about this geometric deep learning? Okay, and you can use A, C, P prime, etc. Okay, so now the questions that I have here, right, is that going back to my wish list, is that this by construction is still going to be invariant. And it turns out that the stability basically will depend on the choice, right? And this will also be good, right? Because they depend on the architecture. Okay. So any questions? Otherwise, we're going to go a little bit more into the detail. Okay. So now let's go back to the scattering transform as here blueprint for the translation. Okay, so when the domain is R2, and so X, we just saw that it's like the functions that are, let's say, have finite energy, right? So this would be just functions that are defined over the plane. And then G relation group. So recall the notion of deformation stability. Okay, so we discussed like what is the natural way to, concretize to formalize the property B, right? So remember that we had this transformation, diffeomorphism from R to R2, that was a diffeomorphism of the form of U minus some change of variables. And then, so the deformation stability for the translation group was of the form phi is stability deformations if phi of x minus phi of this transformation that we call delta of x is proportional to some constant that doesn't depend on x nor the tau times the norm of x times a deformation cost, right? And let's try now to recall what these objects are. So L tau of x is the change of variables. So basically, it's just x of phi minus 1, sorry, of phi, x of u minus star of u. Right, so this is a warped input, and this deformation cost so we illustrated how to define it, for example, using something that looks a little bit like a Dirichlet energy, but so it's like the norm of tau, and this is like the super so that right. So this is kind of measuring how far this change, this transformation is from the translation group. So in pictures, we had this like the space of diffeomorphisms. It was very large, right? There's a lot of diffeomorphisms, and then there's a little tiny manifold that this is just the group, right? The translation group in our case. So morally, we have a point, a diffeomorphism. This distance here is what is measured by this quantity, right? That's kind of the kind of idea that the intuitive idea. Okay, so these are just things that we saw last week. So I guess the question for us is that, well, we saw this this geometric deep learning blueprint that was kind of very axiomatic, very nicely laying out for us a sufficient condition, right? Like a construction that can certify that the resulting features are going to be invariant to the group. Just by observing, it's very simple observation, right? Is that if we compose an equivariant map with an invariant map, the composition is invariant. That's a kind of immediate, like a straightforward property. But now we need to ask the question about stability, right? So basically, how to use the blueprint to obtain stable representation. And so here you can see that the conditions for the blueprint to give me invariant features are incredibly loose, right? So for invariant features, we only needed to use, like, so for translation, if we pick A, remember that was the linear invariant translation, right? So what is the operator, if you remember? It's like a linear invariant. This is just A of X, basically integrating over the domain, right? This is the average for the sum. Okay, so the choice for A, there's no choice, right? That's the only operator that is linear invariant. So now for B, so I ask the question. So what are the linear operators that commute with translation? So anyone has some guesses? So let me just
A rotation.
Not too far, but let me just state it, and it maybe hopefully will become clear. Right. So what I'm asking is B is an operator that goes from L2 of R2, let's say, to L2 of R2, that is linear, and such that B with some translation of some pixels, like let's say T of V of X commutes. So it's TV of B of X for all V and for all X. So maybe Sebastian in his lecture, I guess last week, he told you a little bit about the Fourier transform in the plane, right? Like the Fourier transform in Euclidean domain. And there's many ways to formalize, to characterize intrinsically the Fourier transform. But remember that we used our own way to get to the Fourier transform, right? So we used the route of trying to characterize the Fourier transform as the eigenstructure of a group. So in that case, we know already the answer, right? So we know that we know a way to compute transformations that are linear and commute with translations, just because we know that if we write any operator as having the same eigenstructure as any translation, then it's going to commute, right? We know that two operators, they commute even only if they share the same eigenstructure, but they have the same eigenvectors. So what are the eigenvectors of the translation group? Anyone remembers? So what is it? What is a vector? Let's say vector, let's call it E of U, such that translating its vector gives me something that is proportional to its vector. Anyone? Let's try to visualize. It's important. This is conceptually important. Right? So let's try to visualize a signal, any signal. Let's start with something crazy that it's not going to work. Maybe something like this. Is this thing going to have this property that if I translate it, I'm going to get a multiple of it? Well, obviously no, right? Because if I just move this around, right, I'm not going to get the same thing, right? If I translate this thing. So there's a sense in which any signal that has this property has to be completely delocalized in space. So what are some signals that you know that have this property that are completely delocalized in space? Maybe a wave, maybe a sine and cosine, right? E of U, like actually a complex explanation, right? So if you translate this signal, right, like a complex. So let's translate the signal, theory of E, right? That is E, I, C, U minus V. So what do you get? You get e to the minus I, C, E, then e to the I, psi, U, right? So this is the same as derivation of E. Maybe I should call it differently. Let's call it F. To avoid confusion, right? So these are just the Fourier atoms, right? So what am I saying here? Is that now if I have an operator, an operator that is diagonal in the Fourier domain, then it's going to commute with translations. But what are the linear operators that commute that are diagonal in the Fourier domain? I'm a little bit afraid that I'm losing everyone here. Is this something that you covered a little bit with Sebastian?
Yes, we did.
Okay. So
Fourier, the Fourier
right.
transform.
Okay, so now we just need to kind of close the circle and just to convince ourselves that we just need to characterize to have a good description of any linear operator that is diagonal in Fourier domain. Right, and so let's try to convince ourselves that actually the B linear permits the translations even only if B is a convolution, okay, of the form B x at u is an integral of some kernel that is u minus b x of b. Okay. And so you can verify, right, that indeed, if I express this operator b in the Fourier basis, right, so I know, and we can write it as x convolved with the current, right? So we can verify that indeed bx in the Fourier domain is the Fourier transform of x times a diagonal operator, right? And this is the diagonal of the Fourier transform of the kernel, right? So this becomes the eigenvalues of P. Okay, so this is sometimes called, I don't know why, they call it the convolution theorem or something like this, but I mean, there's really no theorem, right? It's just verifying the definition, right? So this is the convolution is diagonal in Fourier. Okay, so I think we are a little bit, okay, good. So we know that in our blueprint, if we take as B any convolution, right, just to summarize, we have seen that if we consider, let's say, in this K here is any kernel, right? So K is any function that is, in that case, just a square integral. Sorry, absolute integral, right? So if you just take any kernel, any function K that that has finite absolute value, then you can formally define this operator and you are good to go, right? So if we consider any convolution operator, operator B, then, and sorry, and C, any element-wise nonlinear transformation, then this phi of x that is defined as first applying B, then applying C, and then applying A is going to be translation invariant, right? That's what we have seen. But the question is, amongst all these choices, which one is going to give me the stability? Right here, I'm giving you a lot of choice, right? I'm giving you can pick any convolution, any element-wise nonlinearity. Don't worry, things are going to be translation invariant. This is too loose, right? There's among all these choices, which one is also stable? So which is the choice? In particular, the key, like the large, the really like large choice is really the choice of convolution operator, right? Like the class of filters is basically much larger than the class of like scalar functions, right? Like if you think about element-wise nonlinearity, it's just defining an activation function, right? It's like a function from R to R. But the space of all possible kernels, right, is defined in a larger space, right? So this is the big choice. So which one is going to give me the stability? So it turns out we don't know, we don't have a complete picture of characterizing all these operators that are stable, but luckily we have found one family, right? So remember, we call the little belly wavelet operator. So remember that we define it as the mapping that goes from X to actually a family of many filters, right? That we're convolving X with wavelet at different scales and orientations, and complementing it with the low-pass filter. Okay. And so stability here, right? So let me also convince you, how can we actually get stability in the context of the geometric deep learning blueprint? Okay. And so, yeah, like if we want to, so before connecting it to the wavelet, before connecting it to the wavelet, let me also give you the one last ingredient that you need, is that remember from this point, right? What does it mean? We want to have the property that phi of X minus phi of the deformation of X is proportional up to the norm of X to some deformation constant, right? That's what we want. So the same way that in the geometric deep learning blueprint, we took individual properties of the components, and then we can combine them together to get the property of the composition, right? Like how the invariance of the parts gives me invariance of the whole. So does the same question apply for deformation? So if I have stability in the parts, do I get stability in the whole? That's kind of the question that we are going to use here, and just convince you that that's the case, right? So the question is, can we get stability in the representation from stability in the component, right? So the claim is that if A is such that A of A minus A with L tau is smaller than the deformation, and L tau B minus B L tau is smaller than the deformation, then phi that is A C B is stable. Right? And this is really the same logic as before, that if I have stable things, I can compose them together and preserve stability. And let's just check this property. And I need, I guess I need also some, I need unicity. And I need, let me just say that this is going to be a operator that is unitary. This is going to be unitary. Okay. These are the properties that I'm going to use. So let's check that. We need to compose these three operators. ACB minus ACB delta. We like this thing to be small. Okay. So what do we do first? So what we can do, right, is we can start using the assumptions, right? Okay. So let me just also say that. Let's see. Okay, just make sure that everything is contracted here. So now we need to add and subtract one term, right? So this is the same as A, C, delta B plus minus sorry, I forgot one term. Minus AC delta of B. Okay. Now we apply the triangular inequality. So this is the same as A, C delta of B minus A, C, B delta plus ACB minus AC delta times B. Okay. And now we can just start playing with each of the terms. So we can also use the fact that A times B is smaller than A times B, right? An operator norm. So this is the same as is controlled by AC times the norm of L tau B minus B L tau plus AC minus A C L tau times the norm of B. Okay. So for the first term, we are already good, right? Because the first term, right, we know that this term is small, right? Just because the operator B is assumed to be stable. We also know that C, of course, C pointwise implies that C with L tau is equal to L tau of C, right? There's no error. There's no commutation error here, right? Because the operator is pointwise. So we can pretty much just write it as L tau MC. Okay. And so now we can just write it up as here A tau. So we have something that depends on AC times the norm of L tau B minus B L tau plus A minus A L tau times the norm of C times the norm. So now we are good because in each of the decomposition, there's at least one of the term that is small and the other one is not blowing up, right? I'm just assuming that, you know, the operators here, they are not going to be too large, right? So in this decomposition, as long as I have one term in each of the one factor in each of the terms that is small, then I'm good. Okay. So hopefully you have seen that the same way that in the blueprint I can start playing with invariant and equivariant maps to build invariant structures. I can also say, now I'm going to start playing with stable maps and compose them together and preserve stability. So recall from last week, from last lecture, sorry, that we just saw that A minus A L tau was smaller from gamma tau, right? So remember that that's what we show, right? That we just look at as an exercise to compute the kernel of this operator and use the Schur lemma to bound the spectral norm of this operator, right? So we saw it from last lecture. So we have one of the terms, right? So in this kind of wish list, right? So this one is check, right? So now the question is, of course, how can we find a family of convolution operators B that has this property that is almost commuting with deformation? That is much harder. But as it turns out, I mean, that's the whole point why we made this build up last week, is that in fact, there's a result from Stefan that says that, yeah, that there exists a constant such that for any choice of scale, we have that the little bit Bailey transform that I defined here before, right? Lambda smaller than J. Let me just pull this thing back so that we don't need to go up again. Yeah, let me just put it here. Right. So what we know is that this operator, this family of filters, satisfy that Wj times L tau minus L tau Wj is smaller than some, doesn't matter for us here, but there's a deformation cost that is not exactly the one that we saw last week, but it's basically the same. You don't need to worry about the details. Okay? So this is very, like, in other words, like the consequence of this result is important, right? Wavelet convolution, wavelet filters are not only equivariant to translations, which is a trivial property, right? Because just by a convolution, you have this property, right? As any arbitrary filter. B, but also stable to near translations. Okay, and this is really the kind of the instrumental properties that is like basically leveraged by the scattering transforms, and also somehow underpinning also why we have this structure in convolutional neural networks where the filters have localized spatial support and spatial support. Any questions about this result? let me ask a question for you. Do you think that this result is optimal in the sense that could there be maybe another convolutional operator that does even better in the sense that there's no error at all, right? So like, can you find a family of convolutions that are exactly commuting with the formations? Think about it for a second, right? So could we hope to get exact commutation to small deformations? And maybe with this question, I'll take a couple of minutes break. Just thinking about this question, and then we're gonna resume in 2 minutes. Okay, so I hope that you could think a little bit about this question. Obviously, the answer is no, because this would mean that you have a convolution that commutes not with a small deformation, but with any diffeomorphism, right? Because you can break a diffeomorphism as a composition of very small deformations, right? And so the diffeomorphism group is just too big, right? There's no linear operator that can commute with all of them. Okay, so basically the stability is the best you can hope for. Okay. And so let me just give you the intuition why this result is true, right? This result is true. So and it's really about understanding very well the argument, like the kind of the main defining property of this wavelet operator, like this wavelet convolution operator that we have introduced, is that it has this very particular trade-off between the spatial localization and the frequency localization, right? So now remember, like the wavelets, right? So wavelets have a characteristic, let's say time, frequency localization. Okay, so this is let's say time or space, if you want, and this is frequency, right? There's basically 3 paradigms, right? Or there's 3 extremes. The first extreme is just to stay at the, let's say, the representation in terms of the pixels, right? Like the pixels, or like the, you know, the timestamps, if you want, they are very localized in space, right, in time, but very delocalized in frequency, right? These correspond to the Diracs. Right? So these are Dirac. Okay, it's a signal that is super localized in space, but very delocalized in frequency. The complete extreme are the sines and cosines that we just saw, like the eigen functions of the translation, which are the Fourier atoms. Okay, so these are the signals that are completely delocalized in space and have an extremely sharp, basically a completely localized frequency characterization. So wavelets have this very characteristic trade-off that basically they are either they come in different, let's say, aspect ratios, but the point is that we can have trade-offs of this form, right? So I have boxes, right, where this trade-off, like this, the spatial localization is traded off with the frequency characterization, right? So I can have wavelets that are very high frequency, right? So the more high frequency they are, the more, sorry, that's actually a mistake that I'm putting here. So if I think in terms of high frequency, right? So I have, if I have something that goes very high frequency, it's very localized in space. If I have less frequency, I can have something that is more and more localized, and etc., etc., etc. Right? And I mean, this is not the topic of today's talk, but there's all these like a fundamental trade-offs, right? There's a what we call this uncertainty principle that you cannot express, you cannot represent with arbitrarily small precision, both in frequency and space. So somehow the wavelets are in this what we call Pareto frontier, right? So like they are kind of exhaust this trade-off. And so the scale, right, is what is allowing you to move in this Pareto frontier, right? And in that sense, the Dirac and the Fourier are the two extremes, right, of this Pareto frontier. Okay, so the point is that now we are going to see what happens at different scales, right? So let's look at, remember that this level 2x is a convolution with a large family of wavelets. Okay, and so we can break what happens into different regimes. So we can first look at the regime at small scales. Okay, so let's look at the wavelet that would correspond to more like the high frequencies. So there we have now two objects, right? So we need to understand this object, right? So we need to look at let's look at this operator that just looks at one of the convolutions, right, with the wavelet. And we have the other operator that is just doing this deformation. And we need to understand how these two operators interact with each other, right? So this is B lambda and L tau interact with each other. So we can basically plot the objects, right? So just to get an idea, that's making my wavelet at small scales. It's a little wave that is sitting somewhere here. And then I'm asking the question, I try to understand how it interacts with the deformation, and I can try to plot this tau of u, right? This tau of u is basically, in the case of 1D, it's just a scalar function, right? That is modeling some deformation. Maybe just write it like this. And remember that I'm interested in small deformations, right? So this means that, remember that this quantity is small. Okay. So this is basically just telling me that this deformation is smooth, right? That's because the norm of the derivative is small. So I have a wavelet that is I'm looking at what happens at the small scales, and I need to interact to understand the interaction with the change of variables, where the change of variables is very smooth. So obviously, the wavelet output, right? So if I look at the output of this model, this is the integral of x at u minus v times psi lambda of v dv, right? So the output of this operator at pixel u, it only cares about what happens in the support of the wavelet, right? Because you can see that this integral, it's only going to matter in the locations where this wavelet has some energy, right? So in that case, all the action happens in this region, right? So what happens in this region, right? And you know that this region, like this interval, is proportional to 2 to the j, right? So like the scale of the wavelet, like the spatial support of the wavelet is proportional to the scale in which I'm dilating it, right? So it's proportional to 2 to the j. And so the point is that I have some interaction, so I need to understand how this deformation, like how does this deformation look like at the scale of the wavelet? As you can see that what happens is if I have a function tau that is very smooth, and I look at this function that is smooth in an interval that is very tiny. So if this interval is very, very tiny, what happen? What do you think I can do? What kind of approximation I can make in terms of this deformation? Well, for as far as the wavelet is concerned, it only sees tau in this small interval. And a smooth function in a small interval can be very well approximated by a constant function, right? I mean, if the interval is sufficiently small, right, tau of u is going to be well approximated by basically a constant approximation. So for as long as the wavelet is concerned, this deformation looks like a constant. And what is a constant? What happens when tau is constant? Here. How does this L tau look like when tau is constant? If I replace here this dependency, what does this thing become? A translation, right? And so we know that if tau was constant, then the commutation error would be 0, right? Because the wavelet is a convolution. So if the scale of the wavelet is very small, I can already see why this commutation error will be small. Just because for the purposes of this particular filter, the only thing that I extract from tau is that within the support of the filter, I have a good approximation as being constant, right? So basically, just to summarize what I'm trying to say is that at small scales, this filter has support proportional to the J, like very small. And so, and I know that for U and V that are in the kind of the support of psi lambda, then psi minus U minus psi minus V, right, is proportional to 2 to the J times the gradient of tau. Okay? And so I can basically leverage this property to show that the commutation error for this particular output is small. There's another regime, right? So those at coarse scales, right? So when the scale is very large, okay, I have the opposite problem, right? At coarse scales, okay. Now I need to understand what happens when my wavelet, right? It's very, very coarse, right? Like something that is very smooth, right? Then we need to remember what happened last week. Remember what we saw as the example of the in the Fourier case, right? When we looked at the effect of a little filter, like a little modulated window, as we applied a deformation. So remember, what was our conclusion? Is that what was the source of instability, right? So when we look at how basically how if I took a small window, like a Gaussian window, and I moved it in Fourier, and then I applied the deformation, what was the source of problem? The source of problem was when I was trying to put this energy very in the high frequencies, right? Because this is where the high frequencies are those where the deformation is becoming more aggressive. So the point is that if I look at the coarse scales, just imagine what it means, right? So I have one of the filters that is just extracting the very smooth components of the image, right? So think about an image that is very smooth, like very blurry. And now think about applying a small deformation to a blurry image. Do you expect this thing to be very, do you expect the errors to become very large or not? No, right? Because by definition, the smooth, like the low frequencies of an image are stable to deformations, right? That's what we saw last week, right? That all the problems of instability deformations happen at high frequencies, right? Across scales, basically the smoothness of the signal basically dominates. Okay, so this is really different from what happened at small scale, because in the small scales, it's the smoothness of the field that dominates, right? Okay, so you really have this very intricate and, in a sense, beautiful interplay between the regularity that comes from the signal and the regularity that comes from the deformation. So if you look at this filter bank driven by the wavelets, right, you have that you can basically patch, like extract stability, obtain stability by really treating differently the high frequencies and the low frequencies, right? At the technical level, so that if you really want to understand basically the meat, like the technical substance of this result, is really that, just to summarize, right? We have basically that we control the commutation error by breaking into two regimes. Okay, like basically the scale of the wavelet becoming much smaller than basically the scale or the regularity of the field. View. And the other one is basically on when the smooth region, right? On the and then that's not all, right? Because when you have like if you write down the commutation kernel, right, like the kernel of this operator, right? Basically, you are separating it into two parts, but we still need to verify that these two components do not interact, right? Like basically that they are near orthogonal, right? And then there's a last ingredient. Basically, different scales interact with. And just for those of you who are familiar, the sense in which this interaction is taken weakly is in the sense of what's called like the Stein or the Kotler-Stein lemma, right? Using something that is called so this is basically a pretty sophisticated technique from harmonic analysis that says that when I have a bunch of like an operator that is composed as in terms of different operators, the norm of their basically gray matrix, right? The norm of the, if I want to look at the norm of the the joint operator, I can bound it in terms of individual norms, right? So think about like you have a matrix that basically like you have a matrix, right? That can be seen as a fat matrix that has different submatrices, right? The point is that you have something like this, right? So you have a very large matrix that here contains the fine scales, and here contains the coarse scales, right? And you would like to see that the operator norm of this big matrix is small. And I know that the operator norm of this matrix is small, and the operator norm of this matrix is small. So how do you conclude that the operator norm of the whole matrix has to be small? Well, it's not all, right? Because you could imagine that maybe there's some signal for which I can get contribution from everyone, right? And then like basically I'm piling up small norms to get like something that blows up. But this cannot happen because basically the things of the property that is the near orthogonality property. So this is like a pretty delicate result, and it's actually at basically the technical heart of the scattering transform. Okay, so this is really a not trivial result. Okay, so let me just move on. And so, any questions about this result? No. Okay. Good. So, all right. So how can we read out or interpret this result? It says that basically so this deformation stability result says that deformations in the input domain, right? In the input are approximately mapped to deformations in the wavelet domain, right? So you want to think in terms of like a committing in terms of a diagram, right? So we have X. We can apply two things, right? We can apply our deformation operator. Or we can apply our wavelet convolution operator. Right? So basically the point is that this diagram, what we are saying is that it nearly commits, right? So that this thing, if I apply this deformation after applying wavelets, that this is nearly committed. Okay. So now we are done, right? Because now we are ready to define and to present the scattering representation in the translation. Okay, so we have already characterized. So we have characterized so far A, that is the low pass stable invariant. We have characterized B, that is equal to the wavelet transform. The stable linear equivariant. And so what is left, the only thing that is left is like a minor detail, is how about the element-wise nonlinearity, right? So for C, which is the element-wise nonlinearity, we can use, really, you could use anything you want, right? But just for simplicity, we are going to consider what is the element-wise nonlinearity that is unitary, that preserves the norm. So for this, we are going to use the absolute value, right? So we pick rho of basically C of X, that is just the absolute value, right? So that C is unitary, right? Like this operator is nonlinear, but it's like a unitary and contractive, right? And so we also know that C of X minus C of Y is more than X minus Y. Okay. So now we have everything, right? We have A, B, and C. So how do we construct the invariants? Like the schedule. So we start from X, that is our input. So the first thing that we can do from our input is to extract the first set of good coefficients, information that is stable and that is nearly invariant. So we can do it with a low-pass filter, right? So we apply our operator, let's go J, that is convolving with a low-pass filter. Okay, so this operation is just looking at the low frequencies, right? So what is the information that is lost by this low-pass filter? So how can we complement this information? How can we recover the information that is lost by the low frequencies? Remember what we described on Thursday. Right, so what is the information that is not in the low frequencies? It's the high frequencies, right? And so from what we have been saying, we have a filter bank that recovers this information. No? No one? Well, we have been using this for a while now, right? So this is just the wavelet details, right? For all the wavelet coefficients. So this, we know from the Littlewood-Daly transform that these filters are complementary to this filter, right? So they recover the information that is not captured by these elements. So this is our invariant. So this is AJ. This is our operator B. Right? Now what do we need to do? We have to apply C, right? Which is the element-wise nonlinearity. Now we can produce again new set of coefficients, an extra family of invariant coefficients, right? By applying A again. So here now we have the family of new coefficients that are stable, they are invariant. And now we can use the same logic as before. So we have, every time we apply a low-pass filter, we are only keeping the low frequencies. So how can we recover the information that is lost by the low frequencies? By applying an extra, again, the family of wavelet filters, right? So we apply again B. But now we apply it to every of the outputs of the first branch, right? So now we have a double index, right? So like for every of these functions, we apply a new wavelet transform, right? A new index, right? And we apply again B, so I can just write it directly B and C, right? And then we can keep applying AJ and keep going. Okay, so really you can think it is as a tree if you want, right? So we have an input X, we have an output that is the low pass, and we have a bunch of filter banks that complement the low pass, right? These are different scales and orientations. For each of them, I can extract new low pass filters. Let me just maybe change the color. This is the blue is the output, and I can extract new wavelets all the time. Okay, so these are basically F involved with sine lambda, and this is the etc. Okay, so that's the scattering. Okay, so maybe as a more formal definition, right? So we can define what we call a, like in this tree, right? So we can continue this tree. So the way we index this tree is by a path, right? The following this tree. So for each path, we can index it by a sequence of some bands. With lambda I that becomes to the family of indices that we described last week. X. Scattering transform of X is defined. It's written like this. Okay, so this is a signal that is defined as taking X, convolving it with the first wavelet, applying the modulus, then I convolve it with the second wavelet in the path, apply the modulus, and I keep going until I convolve it with the last wavelet. And then at the end, I just extract the low frequencies. Okay, so it's really, you can think it as a family of coefficients that are obtained by repeating the same operations many times. So what are some of the key questions that that evolve around the scattering transform? For example, how much information is contained in scattering coefficients? I mean, this is not very precise, right? What does it mean, how much information, right? So basically, we want to have a sense of, are we preserving all the structures of the input, right? So can we reconstruct the input from the scattering coefficients? And another question, of course, is can we, and this we already know it somehow, the geometric stability. Okay. And so for the first one, we can define I can maybe tell you a little bit about the in terms of like the amount of energy that is contained, like the amount of information that is contained. And for this, we need to define just one extra thing, which is that this representation somehow you can think it that it's indirectly defining a metric. It's defining a way to compare input signals. Okay, so this is the scattering metric. Okay, so this has a definition that is, I guess, the most natural, right? So because we are going from a signal in L2 to a bunch of signals in L2, we can define it's not an Euclidean norm, right? So for a given set of paths, gamma, the Euclidean norm defined by the scattering coefficients is basically aggregating all the L2 norms of all the paths that are in this set, right? So basically, I just look at all the paths that are in the set, and because these signals are in L2, and there's a basic thing that if I have a function that is in L2 and I convolve it with a function that is in LP, right? There's something that is the Young inequality that basically belonging in L2, if I convolve it with functions that are integrable, it's still an L2. So basically, I can always assume that I'm in L2. Okay, for X. Okay, so this turns out that it's well defined. And it's well defined because of the, again, this is a basic fact. So this metric is well defined. Thanks to the Littlewood Valley basically construction. So if you remember, that if I have this mapping, that we remember that it's if I had this W of X, right, that was just X convolved with J and X convolved with all the wavelets satisfies so to remember that we had this property. Okay, so because every time I apply this new layer of my transform, I control things in L2 norm. This is what allows me to compose it as many times as I want. Right? Okay. And so in fact, there's another fact. There's also an immediate consequence of this property of the Littlewood Valley, is that in fact I can look at all the basically I can look at all the paths, right? So like if I say if Pj is the set of all paths, okay, so basically I just look at Pj, that is the union for all M of taking all the transforms. Okay, so basically I look at the full tree. And these are paths of length M. Okay, then Sj of, let's call this like a Pj of x minus Aj of Pj prime is in fact a metric that is weaker than the original metric. Okay, and to show, so this is like a, so basically main tool used a little bit better. Okay. And there's something even more interesting. Not only the fact that this scattering representation defines a metric that is kind of dominated by the Euclidean metric, there's something quite interesting happening in terms of energy conservation. Okay, so that's something I was just going to mention it briefly. So consider now unitary records. So what does it mean, a unitary wavelet decomposition? It means that in this formula here, the case where delta equals 0. Okay, so let me just precise it. A transformation, there is like a linear transformation. Such that the Euclidean norm is preserved. Okay, so it's like think it as a unitary, it's a unitary linear transform. Okay. So now think about what happens with the scattering energy. Okay. So the first level of the transform, scattering transform, replaces this guy, x, produces this output, and then produces a bunch of, basically the first applying one step of our transform just replaces x by this, each of these paths. Right? So remember, in the transform we had the output was the low-pass filter, and then we have a bunch of new signals that are obtained by just the absolute value of this guy, right? And then we are repeating the same operation by replacing this point here by each of the leaves of this tree. But now if we look at this formula, right, we can now reapply our Littlewood-Pelly transform in each of these terms here, right? So we can again we can write this thing. You allow me to write it as the modulus and then the norm, right? By putting the modulus here, I don't change the norm, the ultimate, right? Now I can just, if I call this signal here, I can call it if you want, I can call it x lambda, right? And I have the same thing again, right? I can look at x lambda squared and write it as x lambda convolved with phi j squared plus the sum for lambda prime of x lambda convolved with lambda prime squared, right? And you see where I'm going, right? Now I can look at this and I can call it x lambda lambda prime, and then I keep going. So what I know is that what this is saying is that for any m, the input norm of the signal can be written as the sum of all the scattering paths up to length m plus the residual. The residual is basically just collecting what I have at the last level, right? The last level of the transform, which is just the Euclidean norm of x. Let's call it xp, right? xp it's just applying the one. Okay, so it's the transform without applying the low-pass filter. And so you can see where this is going, right? Is that the question is there some choice of the wavelets for which, as m increases, this residual goes to 0. If this residual goes to 0, it means that eventually all the energy of the signal is going to be captured in the scattering coefficients, right? So if the limit when m goes to infinity of this sum is 0, then we have energy conservation, right? And in fact, there's another theorem by Stefan, 2012, and also some refinements by Ivan later. That's the case, right? So for an appropriate unitary wavelet, we have energy conservation. And moreover, with exponential convergence. In other words, this term here, the residual, this term here, goes to 0 exponentially fast, right, in m. So why do we care about this result? So the reason why we care, right, is that what it means is that in practice, when we try to use these coefficients in practice, if someone tells you that, you know, the relative contribution of these coefficients relative to the rest is tiny, it means that in practice you don't need to keep transforming, right? So in practice means that in practice we can use basically m equal to, right? M equal to is the kind of choice that we use in all the applications. And this basically means that you're already capturing most of the energy of the signal, right? And there's also, but there's of course one aspect, right? So keep in mind is that energy conservation, it's not the same as basically preserving energy, preserving information, right? So I hope that you agree with me. For example, let's say that I have this transform phi of x that is just computing It's just replacing a signal by one number. And this number is just going to be the norm. Right? So obviously this representation is unitary. It conserves the energy, but it throws the information, right? It just collapses everything to one point. Right? So here, when we talk about energy conservation, we are not claiming that you can reconstruct the input, right? That's not true in general. What you are claiming is that you are not throwing away high frequency information, right? Like the presence of high frequency information of high frequencies is still felt in the transform, right? But it's not, formally speaking, it's not a guarantee that you are keeping information, right? It's just more like an indication. Any questions?
I have a question.
Okay.
So this m equal 2 would be, for example, the number of layers, transformations that a network is performing.
Very good question. Thanks for asking. So indeed, so here there's another important, nice, very remark that is related to this, is that in scattering, the m, basically the number of layers, is equal to the number of nonlinearities. Right. So remember in the transform, right? So I have some x, and then I apply this low pass filter because it's something small, and then in the first layer, I have different wavelets at different scales, right? So I have some wavelets that are very, that extract like very fine details, and some other wavelets that extract very coarse details, right? So it's not the number of scales. So, and this is very different from a convnet, right? So in a convnet, somehow, if you think that you are using filters that are all the same spatial scale, the number of layers in the CNN is equal to the number of scales that you can process, right? Layers, so basically in the CNN, the number of layers is always tied with the number of scales. Okay, it's also tied to the number of steps that you will go through a nonlinearity. But in a CNN, every layer of the transform has filters that are all at the same spatial resolution, same spatial scale. That's different from the scattering transform. So that's a little bit of a, yeah, so this is a little bit of a slight difference, right, in the way we present these, organize these computations. There's a way to factorize any of these wavelets, right? Even if a wavelet is like very coarse, to think it as a cascade of convolutions of the same filter that you apply several times. And then you can like really get the same structure of the CNN. But the way it's presented is slightly different. Thanks for asking, right? So m equals 2, it means that you do 2 layers, but you can still have coefficients that at the output have seen the whole image, right? Does it make sense? Does it clarify the question?
Yes, thank you.
Okay, great. So actually, I think I'm gonna just try to wrap it up here today because, and then maybe just use Thursday to basically describe some of the extensions of the scattering to more general geometries and also use it as a way to conclude the class. Let me just finish today by just giving you kind of the punchline, like the main takeaway here is that we have this also like the scattering geometric stability. Let's just have it as a formal result. Right? And there's a theorem. Is that again, it's constant such that for x that is in L2, and all M, the mth for the scattering satisfies M. And then this is the deformation still. And then, sorry, this is times M. Okay, and so this is really no surprise that, but from what we have been building up, right? The reason that the proof architecture of this is because, remember, like the proof is exploit the fact that this it is a wavelet decomposition nearly commutes with deformations, right? And so you compose it as the way I tried to explain before, and you get the result. Okay, so so basically, so next Thursday, right? So this Thursday, sorry, next lecture. Basically extensions of GDL blueprint to non-Euclidean. And I think what would be great is if we could also have some kind of a discussion, conversation, right? And like all of you have been following the class on you know, open problems and open discussion, right? Open discussions, so that I can also get a sense of what you guys are interested in and what did you take away from this class. Okay, so with that, I'll thank you very much, and I'll see you on Thursday.